Hello everyone, and welcome to the Geodynamo Lab. First thing you see when you come in here is a cube which houses our experiment, as well as a sodium tank which is empty right now but eventually will be filled with sodium. And back here we have a shed which also has the controls for the experiment. So we'll get a closer look. We can all kind of squeeze in here because, well, it's just me. Alright, so what we have here is the 3-meter spherical cuvette liquid sodium magnetohydrodynamic experiment. So let me break that down for us. It's spherical, as you can see, 3 meter in diameter across, and the cuvette part indicates the type of experiment where differentially rotating boundaries are acting on a concentric differentially rotating boundaries are acting on a fluid within. So we have a sphere inside here whose radio radii is comparable to Earth's outer core boundaries. So when we rotate these spheres, they can rotate pretty fast. For example, this outer shell can rotate at a rate of 4 hertz. So that's 4 revolutions per second. In that case, we're in the shed. But when it does that, the fluid predominantly wraps around in this direction. So the fluid is sodium, which is heated up to become a liquid, to hot, not too hot, about 115 degrees Celsius. And it becomes viscous, kind of like water, but we'd never mix it with water because that would create a big fire. So while this experiment rotates, we also have a magnetic field applied by these 2 electromagnets situated in the upper and lower hemisphere. So we run a current through these magnets, and that creates a magnetic field that kind of goes in this direction. Okay? So we use sodium because it's conductive metal. That is, when we have the magnetic field go through this liquid, it also wraps in the direction of the fluid motion. So it becomes entrained in the conductive fluid. So the magnetic field is also wrapping in this direction. But what we'd like to see to create a dynamo is that the magnetic field, because of turbulence, wraps back in this direction and combines with the initial applied magnetic field, as you would have in Earth. So this calls for some upgrades in the experiment, which we're currently in the process of working on. The last thing, and the most important thing for me, is the observations or measurements. So currently we have 31 magnetic field or Hall probes on the experiment that measure the radial component of the magnetic field. That is the magnetic field going out of the experiment at 31 locations. So what I'm doing through the process of data analysis and data assimilation is thinking of proposed placements and numbers of magnetic fields probes needed to help with prediction of the magnetic fields in time. The last thing we're thinking about adding is something called acoustic Doppler velocimetry, because we don't have an idea what the velocity field looks inside. So this is a technique that's used in seismology to get an idea of what's going on inside using acoustics. So hopefully when we return to campus, maybe in 2021, we'll have this experiment running and you all will get to see it.